Last time, previously, we talked about potential energy. We said that potential energy allows us to follow and predict changes. For chemical changes, we are based upon one of the four fundamental universal forces, which is electromagnetic forces. So in simple, instead of Gibbs free energy, we are using potential energy, and the energy is stored inside of the chemical based on the charge interactions of positive from nuclei, negative from the electron. The potential energy can be raised by having strong repulsion between same charges, plus and minuses, or losing the attraction between opposite charges, between positive and negative charges. So separating the opposite charge, you are raising potential energy, and bring them same charge together, you are raising potential energy. But natural process want to lose potential energy. And that happens when you gained more attraction by bringing the opposite charges closer, and losing the repulsion by taking them away from each other. Throughout the changes, in order to achieve the final state, like final product, the chemical can go through various energy states, like this, that, and so on. So throughout the processes, the chemicals use heat energy for kinetic energy, so they can explore all the possible energy states. So if this was the initial state, that first process is natural. So this process means the opposite charges are coming closer and same charges are going away from each other. And this process is the case, the endothermic process, meaning you have to bring the same charges closer and opposite charges away from each other, making the system more unstable. For that, you need to force them. So we use kinetic energy, or sometimes the opposite, another situation of the potential energy for force the system to go uphill. And it might even go higher than what can be followed by very spontaneous and reaching stable state. Then there could be a very big uphill. If this is the situation with the various potential energy states for a change, when sufficient energy is given, the chemical will travel every possible way, and they will prefer to stay here longer, because this is when they feel most attraction, so it can be most stable. So if that is the chemical reaction, the arrangement of the groups and electrons providing the most attraction between nuclei and the electrons and least repulsions between electrons and proton themselves. However, if you don't give enough heat energy, then the chemical initially start from here and get down there. Then without kinetic energy they cannot come up, so this could be the final state. So this universal minimum energy state can be achieved only the system is given with enough kinetic energy. The change can be size change. When you have a neutral fluorine, it has 9 protons and neutrons in the nuclei, and you have 2 electrons on the first shell, then 7 electrons on the second shell. We talked about details about effective nuclear charge, and there will be a video talking about it more in detail. In neutral state, the diameter of the atom is about 73 angstrom. However, when you inject one more electron onto the valence shell, then the fluorine will be negatively charged. Then the fluoride will experience more repulsion by the electron on the shell. Therefore, in order to lower the potential energy, the electrons must move out a bit. That causes the expansion of the second shell, and surprisingly, the size of the new shell in the negatively charged state happened to be 126 angstrom. It's a big change. This way, you can understand the periodic table better. The trend of the size of the atoms in their neutral state was like from left to the right, the size of the atom decrease. That's because now you know, for example, the second shell elements, they have 2 shells, and you are putting more plus charges as you walk from here to there. Therefore, more attractive force for the electron is exerted, so these shells shrinks. Therefore, the size must decrease. But when you move to the third shell, then you have a sufficient electron to fill all 2 inner shells, and you end up having another electron there in order to avoid too much of a repulsion on the second shell. Then you have extra distance built. The same trend for the elements on the third shell applied. You walk from this end to the other end, you have more protons, therefore attraction increases and the shell size decreases. Electronegativity was also same trend, because electronegativity is basically caused by mainly the positive charges from the nuclei. We also talked about the role of potential energy in bonding. First of all, electrons on the valence shell, they are somewhat stable because they are attracted. But when you bring 2 atoms close together we said that there is a certain better area for electron in terms of stability, which means more attraction. That was the middle section. So when you imagine a molecule with an atom, the atom is seen as a round particle, and on the surface some of them go inside deeper, but most of them make a certain thickness of the crust, and that's where you find electron in the high probability. But before you bring another atom, the electrons are evenly distributed in a given orbitals. But with presence of the other particles, there are sections where you can have differences in terms of attractive force for electron. So the middle section here was the place where the electron field most stable. And any bonds can have 2 electrons at the most. So when they're brought close enough, now they have to determine whether they will share electron, or it's better for one of the stronger guy takes both electron and become ionic bond. So when the electronegativity, which is attractiveness of the atoms, are about the same, then they will share the electron. That way electron feels the most attractiveness from either nuclei. So you can imagine this one like the case you have to use a model. It will look like this. But this is not the real picture, because there is no such shape like rod in between 2 nuclei. So when you picture them, when they're together, mostly look like this. And this, you can imagine that you have central plus charges of the 2 nuclei, and then there is an inner shells, depends on which atom you are dealing with, how many ever there might be. Then the outer shell electron used to be evenly distributed. However, because the central area is more attractive, you get more electron density, and you have a less and less electron density outside. So most of the electron will be found here, and that was a bonding. But from now on, you have to look at this one and imagine it like this, with a stick in between. So like A is bound to the B, then you have a line. So the line is not really there, but what we mean is most of the electron you find is represented as a line. And these symbols indicates how many ever inner shell you might have and how many positive charge from nuclei you might have. You have to imagine it accordingly. Therefore, in terms of potential energy, you can put it this way. The atoms originally had the potential energy for electrons. Then when they brought together, becomes more stable in the bond. And it is exothermic process, so it happens spontaneously and electron like it. In order to go against, which means you're gonna take the electron in the middle away from the most attracted area to the other area, you are breaking the bond. And that's not spontaneous, and you have to force them. And how much energy it takes, you can calculate from the difference between these two potential energy. Alright, now let's move further. Let's assume that you made a bond like this. And this heavier atom, such as carbon, made a bond with hydrogen, and you have a shared electron in the middle, and that's represented as a line, but you have to imagine that it is actually two shells sharing the electron mostly in the middle with the inner shell for the carbon. And when you try to make another bond with a hydrogen, you wouldn't attempt to make this way. Although you are making same type of a stable bonding for the electron in the middle, if you look overall repulsion, you can imagine some repulsion between these two. So you have carbon and outer shell, and you have a pair of electron spending more time here because of the presence of other plus charge over here from the hydrogen. The electron in another bond, they are too close from this angle. But you see, you have another side where you don't feel much repulsion. So what will happen is the repulsion of these two caused high potential energy like this, and they want to push the electrons away. That way they can lower the potential energy, and they go like this. Then if you go further, you are getting closer from this angle, so you are raising potential energy. Therefore, it's going to find the equilibrium angle here as a 180 degree. Then it will stay like this, and which means you have two electron pairs with a maximum distance, so minimum repulsion, and they have a maximum attraction from the both of the nuclei here and there. So that's the best geometry for two electron pairs in the bonding. So this was the case with the two pairs of electrons stuck in the bondings. But in certain situation, you need to make another bond, and you bring in this electron pair. Let's just imagine the process. When you have an electron from the hydrogen far away from the central carbon, they don't feel much because the distance is too great. And as they get closer, the electron here start to feel these, and they are repelled. So for this to react, you have to overcome the repulsion here. So either this go away, or using the heat energy, it keep moving toward it. Then these are forced to move. So what might happen is eventually, to overcome the repulsion here, they have to create more repulsion until the repulsion between these two from this angle equals to repulsion from this side. So as they get closer, they will eventually go like this. And that's the best geometry for the three bondings. Okay, now I have another molecule, This one already has 3 bonds, and these electrons repel one another equally this case, and they achieved 120, 120, and 120 degrees of angles, and it's trigonal planar structure. But when you have to form another bond, say I bring a new electron pair from the top and it's going down, then as you can see, as it gets closer, you have achieved a 90 degree of repulsion, while these electron pairs have a 180 degree repulsion from this through the under the table to the other 2 bonding electrons, and that's not stable for them. So what they want to do is they want to release this repulsion where you find the 90 degree angles by increasing the repulsion between this and from the other side, like bringing electron closer to this direction. And the best angle they can achieve is as they go like this, and I hope you can see that's tetrahedral shape. Then you have an equal angle, not anymore 120 but 109, not anymore 90, also equally 109 degree of angle, and you got the perfect tetrahedral with the same 4 groups. Okay, here's another atom with a tetrahedral electron pair arrangement, and let's say this is a carbon. When you have a 1 carbon, you found least repulsive electron pair arrangements and the most attractive possible way for electron from the nuclei, the center of the carbon, their positive charge, by placing the electron in the middle of the bond here, 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 and here. And please don't forget, these lines are not existing in the reality. And more complication comes in when you make a bigger molecule. When you bring another atom, whatever it might be, with a perfect tetrahedral shape, that means most stable potential energy it has. By having the 2, you have a new issues. So the certain awkward angle you had in the beginning of attachment of new bond was adjusted as you change the angle. You are able to lower the potential energy to the best tetrahedral shape for carbon and a couple other atoms. But when you bring these 2 together, you have various arrangement of the electron pairs. This look different from this, and maybe slightly different from this, and you don't see that well. So later we're going to cover this topic, but we can see the change better if you see from this angle. So this angle shows you that you have these 6 electron pairs are at the maximum distance. If you change the angle any direction, you bring the electron pairs too close. So when you have multiple atoms, the individual best tetrahedral arrangement of electron pairs is not the only one you must consider. So let me make the more complicated situation for the real problems. How about this? I have many atoms. As you see, you cannot make the linear arrangement of atom because each atom has 109-degree angle. So the connection cannot be linear unless you force them to be. Then you're gonna break the bond. So naturally, the atom is supposed to be like something like this. Like this. However, like I said earlier, in any temperature, they possess some kinetic energy, each individual atoms in the molecule. So when they start to move, they can go other shape. Especially, say the white ball is attracted by the red ball, like hydrogen, to the oxygen. Then they are destined to fold. And that's more stable because you brought partially negative oxygen, partially positive hydrogen, and giving some attractive force by losing distance will lower the overall potential energy. If this attraction is stronger, then all the repulsions you create in the middle of the chain, because you end up bringing some electron pairs too close, then it will fold. If the attraction between the white ball and the red ball is not strong enough, then the molecule is not gonna fold, and try to avoid the repulsions in the middle section. This complicated balance of the attraction and repulsion to find the best lower potential energy is the key concept in protein folding in alpha helical or beta sheet. Alright, so the original compound with the awkward angle can be adjusted to lower the potential energy, to maximize attraction, to minimize the repulsion. Then we just saw that further adjustments possible to lower the overall energy even lower. But from here, what can happen? Say you store a certain chemical and they are in the most stable form. In a given kinetic energy, in a certain temperature, they're able to change their form a little bit using their given energy as much as they can explore. But when you have another chemical mixed in, what could happen? That's our next discussion. Alright, say you have water molecule. I'm going to explain more in detail about the shape of water later, but say this is the water molecule for now. And the water molecule, as we talked about, they share electron but not equally. The electron feels more stable with a lower potential energy when they are attracted to the oxygen. And I said that makes the oxygen having more electron density than nuclei number, so oxygen will develop partially negative charge. And hydrogen losing electron, so you have a more proton charge than electron charge, so you have positive partially developing. Then you have more than one water molecule. And as you can see, there are two different arrangements of water molecule. And I hope you can see right away that this water with partial negative charge on the hydrogen, it will prefer to have negatively charged the oxygen close by, not the repulsive hydrogen, because that's high potential energy situation. So this water molecule will end up spinning to bring the oxygen closer to the hydrogen and rearranging itself. So they will eventually form strong intermolecular interaction. That's how they lower their overall potential energy, not as a single molecule alone. So that allows us to understand more lower the potential energy by intermolecular force. So you would not imagine this kind of situation where waters having oxygens coming together. There will be very high potential energy situation unless you put something like sodium positive in the middle. Then suddenly you have these attractive forces lowering their potential energy as group, and you can achieve spontaneously low potential energy state. That's how you dissolve and solvate sodium ion in the water. Then we could be curious, when these molecules have interaction, strong interaction called hydrogen bond, why wouldn't they form even more stronger bond like this? Wouldn't sigma bond more stable than hydrogen bond? If you only look at the numbers, it could be. However, you are breaking some serious rule. This is how you figure out whether some interaction turned out to be new chemical change, or it's not possible to have a chemical change but just having physical intermolecular interaction. If you give the attention to the hydrogen is using first shell 1s. The maximum number of electrons you can have is only 2, and the hydrogen already has 2 electrons uses its shell. So additional electron given by oxygen would have too much repulsion, causing too high potential energy, so the electron will be pushed away. So they're not going to form bond, but just having intermolecular interaction to lower overall potential energy. So there's no bonding between hydrogen and another water molecule. That's how you figure out. Okay, here's the example for second shell element. The first shell only holds 2 electrons at the most, but second shell can hold up to 8. That is part of the octet rule for the only second row elements. So oxygen is one of the second row elements. It already has 2, 4, and 6, 8 electrons. So it has full repulsions that can accommodate. But if you attempt to give the electron from hydrogen or anybody else to the oxygen, then you know what that means. The oxygen's having too much repulsions due to the injected electron. Therefore, it's not possible. So they don't interact. They don't form a bond. So this discussion leads us to the big question, one step closer to the real organic reaction. How do you know then if they react or not? If fully valent atom receive electron and then, like we've seen, they cannot react? Not really. The rule is always, if you can give and take electron and able to lower the overall potential energy, then it can react. What do you mean by that? Let's use our favorite example. The hydrochloric acid reacting with the sodium hydroxide. You can see that sodium is not able to compete with the oxygen for electrons, so it donates all the electron to the oxygen. So in the good solvent like water, sodium is separated from the OH minus freely, and you have OH minus holding extra electron on the second shell of oxygen, and these electron is in very high potential energy, and they want to be lowering the potential energy by giving away some electron that will reduce the potential energy. Then they are certainly looking for some attractiveness. So you can see this molecule HCl has electron pulled to the chlorine and having partially positive charge, and that's attractiveness, but chlorine is negatively charged. Therefore, the OH minus is not gonna even go nearby the chlorine because they repel. It will instead head to the hydrogen. Also in the good solvent, you will have H plus losing all the electron and giving it to the chloride, because the chloride will be stabilized by water molecules, by the plus charges on the hydrogen of water molecule stabilizing the ion. Then the hydroxide will head to the proton. So as hydrogen and oxygen come closer, the electron density around the oxygen will be attracted to the middle section of H and the oxygen, as we discussed before, and they will end up sharing electron, and it will turn into sigma bond. So you form water. What's left is chloride ion and the sodium positive. In a good solvent, they are separated by the water solvent, but if you remove the water, then they need to come together to stabilize themselves. By losing distance between opposite charges, you lower your potential energy. So what did you get as final product? These were reactant, and what you get as a product is water molecule and then NaCl salt. Even in the water solvent, negative charge is on the chlorine in the product, and negative charge is on the oxygen in the reactant. And you can see which atom holding electron better with a lower potential energy. Oxygen is second shell element. Chlorine is third shell element. As the shell size increase, the surface area increase by R square. So the distance between electrons, the same 8 electrons on the small oxygen here versus a big shell of the chlorine holding same number of 8 electrons. You can conclude easily that electron distance on this shell is much greater for the same charge compared to oxygen's negative charge electron here and here. very close, much more repulsion, less repulsion, so lower potential, higher potential energy. Therefore, by reacting, even giving electron to the fully valenced hydrogen, they are able to push away electron to the chlorine, end up making negative chloride ion, but that electron feel more attracted, less repelled, therefore they go this direction for the change. Then you broke the bond, you form the new bond, so this is not simply dissolving or hydrogen bond kind of physical situation, but that is chemical change, chemical reaction. So in summary, I hope I showed you that the potential energy, the energy stored in the molecule, is a good guideline to predict and estimate the properties, physical properties and chemical properties. Some physical properties could be polarity and solubility, using the interaction between solute and solvent, and the boiling point and melting point, etc. And the chemical property is basically their reactivity, like acid as and the base. So we'll be talking a lot more on this topic later on. So the potential energy is basically the function of distance between charges. For the potential energy, you also have to consider how much partial or full charges you have, from the nuclei to the overall ion and the molecules. And sometimes you have to look at the angle changes and so on to estimate the potential energy of molecules. So after all, you have to build your three-dimensional perspective to evaluate the potential energy better. Also, the interactions between two different three-dimensional structures, how they interact, and how that different interactions lead to the different changes will be all depends on your ability of imagining three-dimensional structures. I hope this helps. I like to apologize for the low quality of the video again, and I'm not videotaping also with the manuscript, so I sometimes pause too much. I hope this thing get better in the future. So that's it for today, and enjoy organic chemistry.